Hey everyone, and welcome back to The Explainer. Today, we are going to unpack something pretty incredible, the almost magical process of manufacturing an indestructible transmission shaft. We're talking about a technique known as multi-station parts forming, and specifically, cold forging. If you've ever found yourself wondering just how the critical components inside heavy machinery or high-performance cars manage to survive the immense punishing forces they're subjected to every single day without just snapping in half, well, you're in the right place. We're going to break down the exact science of shaping metal so it becomes virtually unbreakable.
Okay, let's dive right into our roadmap for today. First up, we'll look at the quest for stronger shafts. Then we'll map out the actual forging sequence. Third, we're going to zoom in and master the metal flow. Fourth, we'll look at forming the involute spline. And finally, we'll wrap up with the DIN 5480 standard.
Section 1. The quest for stronger shafts. I want you to picture a transmission shaft inside a massive, heavy-duty industrial machine. It is taking on enormous amounts of torque and mechanical beatings day after day. Which brings us to a really high-stakes question. Why do some of these shafts seem to last virtually forever, while others just shear and fail under the exact same pressure? Well, as it turns out, the secret to a long life isn't just about using a really tough raw metal. It's about exactly how we shape that metal. Shape it the wrong way, and you introduce these invisible weaknesses. But shape it the right way, you unlock unparalleled strength.
Just look at this data. This shows the shocking efficiency difference between traditional machining and cold forging for producing the exact same part. If you machine a shaft, cutting away metal from a solid bar, it might take 10 minutes per piece, and your material utilization drops below 35.7%. That means you are literally throwing away over 60% of your metal as scrap shavings. But with cold forging, you form that exact same part in just 3/4 of a second. And because you're pushing the metal into shape rather than cutting it away, your material utilization approaches 100%. It's vastly faster, there's practically no waste, and as we're going to see, it makes a far superior product.
Moving right along to Section 2, Designing the Forging Sequence.
So how do we actually pull this off? When we talk about cold forging, we aren't just giving the metal a single giant whack. We use a massive machine called a multi-station former. Take a look at this transfer mechanism. The whole process starts with raw metal wire being drawn into the machine. It's cut off into a perfectly sized blank, and then this highly specialized transfer mechanism sequentially shuttles that blank past multiple different dies. In just a fraction of a second, the machine moves the part from station to station, striking it multiple times to build up complex shapes that a single blow could absolutely never achieve.
The physical journey of that raw wire happens in an absolute blur. First up, cut off. The machine shears the precise volume of material needed. Second, extrusion. This is where we move material either forward or backward to reduce the diameter or create special features. And third, heading. This is where we essentially upset the material, gathering it together to create a wider head or a flange. Bang, bang, bang. Each station executes a highly specific operation.
Let's look a little closer at that second step, extrusion. Engineers have a couple of main ways they design this. The first is trap extrusion. Now, just like it sounds, the metal blank is completely trapped or fully enclosed inside a die. A punch then forces the metal to flow forward. Because the metal is fully enclosed, engineers can use trap extrusion to force a really massive reduction in the cross-section of the part, though it is typically reserved for when the shape of the part is relatively simple. Now, what's really interesting is the alternative, open extrusion. Here, the blank is actually not enclosed in a die while being extruded. So why do this? Well, sometimes the sheer complexity of the part's shape requires it. The trade-off here is that the amount of reduction you can achieve is limited. The pressure required to push the metal can't exceed the raw material's yield strength, because if it did, the unsupported metal would just buckle and fold. But engineers get around this by using more than one open extrusion step in a row to achieve the final desired shape.
This load diagram perfectly visualizes this exact sequence design in action. You can trace the progressive steps starting from the sheared blank down at the bottom, moving up through the heading operations and finally over to extrusion. Notice how heading is used here to upset the material and form those wider flanges. Sometimes, to maintain perfect concentricity and keep the part from buckling, engineers actually have to split the heading process into two separate, carefully calculated steps. It's this delicate, high-pressure dance. Okay, Section 3, Mastering the Metal Flow. We've seen the mechanical action of the multi-station former, right? Now let's slow things way down and zoom all the way in to look at the microscopic structure of the metal itself. To really understand metal flow, engineers use a fascinating inspection process. They take a completed, cold-forged part, slice it right down the middle using a precision wire cut, and then treat that exposed surface with chemical etching. This chemical reaction essentially reveals the interior grain structure of the metal, making the normally invisible flow lines completely visible to the naked eye. And this brilliantly illustrates exactly why cold forging is vastly superior to traditional machining for high-stress parts. Think of metal kind of like wood. It has a natural grain to it. On the left, you're looking at a machined part. Machining cuts directly across the natural grain of the raw bar. It leaves the grain completely unaltered, but it exposes all those grain lines right at the edges. This creates built-in potential for weakness and fatigue failure right at the surface. But on the right, look at the cold-forged part. The immense compressive forces plastically deform the metal. It rearranges and strengthens the grain structure continuously along the exact contours of the part. This continuous metal flow drastically increases the part's fatigue resistance compared to machined parts. I mean, it makes it practically indestructible.
Section 4. Forming the involute spline.
So, we have this hardened, perfectly flowed, totally fatigue-resistant shaft body, but it needs teeth to actually connect to a gearbox. And the teeth on these splines aren't just random zigzag shapes. They are engineered to an exact, mathematically precise profile called an involute curve. If you imagine a taut string unwrapping from a cylinder, the path the end of that string traces out, that's an involute curve. This specific geometric profile is incredibly efficient for transferring power. And keeping with our highly efficient manufacturing process, these teeth are typically formed through cold rolling. That's a chipless forming process that, just like cold forging, perfectly preserves that vital material grain structure we just talked about. You can see here a handful of various cold-formed components that feature these precision geometric splines and flanges. Now, this level of exactness matters to you and me because this is literally what guarantees the reliability of the industrial machines, cars, and aerospace tech we all rely on every day. When gears mesh with these perfectly formed involute splines, they distribute the torque evenly, which minimizes wear and tear and prevents catastrophic mechanical failures.
Section 5. The DIN 5480 standard.
To make absolutely sure a shaft built in one factory perfectly fits a hub built halfway across the world, the engineering world relies on rigorous standardization. And the DIN 5480 standard ensures universal interchangeability through a few key tenets. First up, it dictates a standardized 30-degree pressure angle for the teeth. Second, it requires a uniform basic rack profile for all pitches. Third, and this one's a biggie, the reference diameters are independent of the module. This is incredibly clever because it allows engineers to easily adapt these splined connections to fit standard ball and roller bearings. Ultimately, that drastically reduces the number of different, extremely expensive tools a manufacturer has to keep on hand. So the really crucial point to take away from this standard is its reliance on something called flank centering. In a DIN 5480 spline connection, it is the actual sides or the flanks of the gear teeth that are pulling double duty. They don't just transmit that massive twisting torque, they're also physically responsible for centering the hub and the shaft perfectly relative to one another. This specific geometric rule is paramount for structural stability, ensuring a seamless, completely vibration-free connection even under immense loads. We've seen how taking a raw piece of wire, orchestrating a high-speed sequence of extrusions, and plastically bending the metal's grain structure creates an incredibly strong, perfectly splined shaft, all with virtually zero material waste. It really makes you look at the physical, manufactured world totally differently, doesn't it? So I'll leave you with this final thought. How might the mastery of chipless forming and microscopic metal flow revolutionize the other components in the machines you use every single day? It's a fascinating area of engineering and one that is quite literally holding our modern world together. Thanks so much for joining me on this explainer, and keep your curiosity sharp.